can start. The floor is yours.
Yeah. Um, Let me know if you can see my screen.
We can see it.
Yeah, right. So, hello everyone. My name is Volodymyr Kuzin, and I'm a master student and at Igor Sikorsky Kyiv Polytechnic Institute. Today, I am pleased to present our research on assessing the impacts on the war in Ukraine on agricultural lands using advanced remote sensing and machine learning techniques. The war in Ukraine has caused catastrophic destruction in the agricultural sector, threatening not only the country's economy but also global food security. In 2022 alone, more than 86 million people in 27 countries suffered from hunger due to damaged and destroyed Ukrainian fields. The main motivation behind this research is to help restore Ukraine's agricultural capacity, which has been heavily disrupted by the war. In response to present challenges, we have turned to remote sensing as a powerful tool for monitoring and potentially restoring the well-being of Ukraine's agricultural sector. Such approach offers several crucial advantages. It enables us to observe vast areas efficiently, provides access to currently occupied territories where ground assessments is impossible, allows us to determine precise dates of damage, facilitates rapid damage assessment, and ensures data transparency, a critical factor in our current global context. Our primary objective has been to develop a cloud-based geospatial system capable of monitoring and quantifying the war's impact on Ukrainian agricultural lands. To achieve this, we have focused on three key research objectives. First, developing new data sets specifically for monitoring damaged fields. Second, creating methods for automated detection of damaged areas using machine learning techniques. And third, developing a geoportal to support visualization and decision-making processes. To implement our monitoring system, we utilized a comprehensive set of data sources. At the core of our analysis are Sentinel-2 stat images, which provide us with regular, high-quality observations of agricultural areas. We have combined this with detailed boundaries of agricultural parcels across Ukraine provided by Synergize, identified within the initiative EU4A. Most importantly, we have developed a null dataset containing 5,537 manually collected and labeled damaged fields, categorizing them into three distinct types of damage: white craters, black craters, and burnt areas. This dataset forms the foundation of our machine learning approach. Our methodology follows these steps. First, we utilize three temporal images capturing the field before, during, and after damage event. This temporal approach helps, helps us distinguish between actual war damage and pre-existing field features significantly reducing false positives. Secondly, we use the V2, V3 spectral bands alongside with GCI and base 2 vegetation indices. The latter has proven particularly effective for detecting burnt areas, which represent a significant portion of our damaged field cases. Third, we have implemented an adaptive thresholding system using random forest regression, moving away from fixed threshold values. This allows us to individually calibrate detection parameters for each field, dramatically improving our accuracy across different conditions and damage types. The accuracy of our damage classification is high, with F1 scores ranging between 0.73 and 0.79 across different types of damage. Thus, our model can effectively differentiate between the various types of war-induced damages, providing reliable data for analysis. As you can see on the images, the use of adaptive coefficient selection allows us to detect both white craters images on the left and black craters images on the right quite accurately. In the case of burnt fields, which are poorly recognized by the method from our previous approach due to their large area relative to the size of the field, the use of the base 2 vegetation index allows for almost perfect detection of burnt fragments. One of the most our significant practical outcomes from the research is the development of VARSCAN, a comprehensive geoportal for monitoring war-induced damage to agricultural fields across Ukraine. This system transforms our theoretical and methodological advances into an accessible practical tool for stakeholders working to address uh, the agricultural crisis. The geoportal has been entirely built on the Cool Earth Engine platform, leveraging its powerful cloud computing capabilities for real-time data processing and visualization. You can check it out by scanning QR code on your screen. But be aware that this was designed for bigger screens than mobile. So, yeah. Key features of the portal include interactive mapping of affected agricultural fields across Ukraine, temporal analysis capabilities, allowing users to select specific dates. Here you can see coded visualization of damage severity, which shows the percentage of the field area that was detected as damaged. Uh, and and on this slide, you can observe detailed field by field damage assessments. In conclusion, we developed a cloud-based geoportal that use remote sensing and machine learning to monitor war damage to Ukraine's agricultural fields. Our classification models accurately identify damage types, and our anomaly analysis helps to detect local damage with high precision. The portal offers essential insights for rehabilitation efforts and ensures data transparency. Future developments will focus on expanding the portal's functionality, integrating predictive models, adding new data sources, and automating reporting for further support Ukrainians' agricultural recovery. This research is supported by the National Research Foundation of Ukraine and the Ministry of Education and Science of Ukraine, with contributions from our international partners. Thank you for attention. I will be happy to answer any questions you may have.
Of course, maybe somebody have questions. Yeah, I have two questions.
Yeah, sure.
Vladimir, first one is it some similar systems? Did you done some research of available other systems? Or your
Mm,
system is the one day? It's first question, and if I can, the second one just now. As we know now that Google Earth Gene plan to do something in their politics of service provision. Did you think about some transition into some other cloud-based services in future, at least? Thank you.
okay, yeah, thank you for the questions. For the first one, yes, there are probably some projects on these topics that actually also collect and visualize uh, damage fields and providing actual monitoring for similar cases. But as far as I know and aware of them, they're like outdated and does not provide mm, such details as mm, our application, our portal, I guess. Uh, yeah. And for the second question, uh, yeah, I'm also aware about new Google Earth engine, and I am sure it's entirely Google platform politics about uh, changing their um, payment or not just payment about resources strategies. So it will be reasonable to move really to another cloud platform, uh, which but like Creatives, for example, yeah, but it will be need to recognize our infrastructure and yeah, think about the ways of providing data and visualization stack for our portal, I think. Yeah.
We cannot hear you.
Yeah,
Volodymyr,
it's a pity. Yeah. Yeah.
Volodymyr, thank you very much for your question. I have one little more. What data did you use for validate your product? It was handmade, polygons, or something else?
Um, I think Sophia will be better to answer that. Yeah, could you?
So we use difference data. For example, we use vector boundaries of fields from the Synergize company, and also we use satellite data like Sentinel-2 satellite, spectral bands, and vegetation indices. We use B2 and B3, this is blue and green band, and also we use NDVI and green chlorophyll index from Sentinel-2 satellite. What we also use, we use some data set that we has manually collected. This data set contain threshold coefficient for each band and Sentinel-2 vegetation indices. And we use this threshold coefficient to identify anomalies in the fields. So this is data that we use.
Thank you.
Thank you very much. I think it's enough here. For maybe some more questions. We have time. So, Volodymyr, thank you very much. Very comprehensive, detailed presentation. Now you know everything about the system. So, thank you very much. So,